Okay, welcome back, everybody. So, yesterday we ended with a way to finally, or at least we were about to see a way to translate these problems, these questions we had originally asked, into a framework that would allow us to solve these in kind of a more straightforward way. So, the two questions, just reminding you again. Now we've been talking about these for a couple lectures. So the first is both of these, of course, being examples of counting when there's symmetry present. So we're counting the number of configurations of some object. Usually we phrased it as colorings or constructing, like a necklace, seating arrangement, however it is phrased. It's a configuration where there's symmetry present that is going to require us, in the context we're interested in, of discounting that symmetry. The symmetry is going to tell us what we consider to be equivalent configurations. Obviously, we need to know that if we're counting non-equivalent configurations, right? So that's very, very important. So, first example, how many ways can King Arthur and his knights sit at the round table? So this is these sort of seating arrangements, and equivalent seating arrangements under this scheme are obtained through rotation. Okay, so if one of these seating arrangements can be rotated into the other, we would call them equivalent. We're counting the number of non-equivalent uh, seating arrangements in this way. The symmetry group is the cyclic group. Um, this is the cyclic group in objects. This is remember, we can think about this as the rotational symmetries on a regular n-gon, right? A regular n-sided polygon. In the case of the second problem, which is how many different necklaces with M beads can be formed using M different types of beads, the idea here was that now we have additional symmetry. So in addition to simply rotational symmetry, we also have this reflection symmetry because we can turn the necklace over and be unable to distinguish a difference in the beads, whether they're turned over or not. And so this provides additional symmetry. We saw that the symmetry group in this case, G, is going to be this dihedral group on n objects. So we saw that this is half rotations and half reflections here. This has order 2n, this has order n. And this is the object now. This is the symmetry group that we're talking about in this problem. So in our formulation last time, we defined the notion of equivalence classes. We saw that in this previous example, I know I'm flashing a bunch of different slides from yesterday. In this previous example, where we considered the set of all possible colorings of the vertices, thinking of this as a 4-beaded necklace, where we didn't consider reflection symmetry. So we were only talking about rotation symmetry here. So the group in question was the cyclic group on 4 vertices, or 4 objects here. The 4 objects, S is the set of the vertices, and in this way we defined what it meant for colorings to be equivalent. This allowed us to talk about equivalence classes, and then our problem could be reformulated as counting a number of equivalence classes. We saw that in this example there were 6 equivalence classes, and so this was our answer to this sub question of how many non-equivalent colorings are there for a 4-beaded necklace using 2 colors, red and green, for the beads, if we don't care about reflection symmetry. So we were only caring about rotation symmetry here. The answer was 6, and this came from our enumeration of the number of equivalence classes that we got here. Okay, and so let's revisit those original problems. Okay, so let's revisit our original problems, which let's do the King Arthur problem first. So we are going to translate these problems into a language that makes them a lot easier to deal with. So, example. Oh, that pin's no good. Let's throw that away. Let's use another pin. So, example here. This is the King Arthur's. So, King Arthur and the Round Table. So in this example, what is the set S? Remember this formulation that we had, this idea that we had for doing this was to come up with our set of objects, to describe what the set of colorings looks like, to describe the group of permutations that represent symmetries possessed by this configuration of objects. And then we're asking the question of counting non-equivalent colorings, where equivalence of colorings comes from this induced map for these permutations, right? So we take a permutation, its induced map on the coloring, it permutes the coloring, or it computes the, we're calling a configuration here in this set C a coloring. So it permutes the coloring in a way indicated by the permutation itself that forms an equivalent coloring to what you started with here. That is how we denote equivalence. And so our problem becomes counting the number of non-equivalent colorings. Okay, so reformulating here, S, what is S? If I'm seating in knights around my round table, right? So let's say we start here. Remember, there's no distinguished position because this is round. And we proceed in this fashion until we have sat in knights around this table. So S is simply the set of in places at the table. So this is positions at the table. Okay. What is G? Well, as we saw previously, G is the cyclic group on these n positions. What is C? The set of colorings. This is the collection of all n factorial seating arrangements. We know that there are, if a seating configuration in this case is denoting what we will call a coloring, right? A seating configuration is denoting that. But a seating configuration on n positions, the total number of those we know is just n factorial, right? This is just the number of total permutations of this. And so C is the collection of all n factorial seating arrangements. Among this entire collection, the question becomes counting the number of non-equivalent seating arrangements. So the number that I'm interested in, n, is the number of non-equivalent seating arrangements, where equivalence, of course, is dictated by whether an arrangement can be taken to another arrangement by something in this group. Okay. The other example, the necklace problem, putting it into terms that we care about. S is again a set of n beads in this case. Our symmetry group now is the dihedral group on those n beads. And C is the collection of, if I can use M colors for any of the beads, and the beads within each class are completely indistinguishable, just by the product rule, there's N slots. Each of them could be colored in M distinct ways, and there's no restriction on how I do the coloring. So this is the set of all m to the n possible arrangements, m to the n possible arrangements of the m kinds of beads on the necklace. Okay, and then n is, of course, the number of non-equivalent arrangements of the beads. Okay. So we've reformulated both of these problems, but the thing is that we are not quite yet ready to state our solution to these problems. We have to introduce a few things first before we can. So some new notation and terminology here will help us to do this. Let's talk about a few of these things. So one, so given a permutation pi in your symmetry group, define C sub pi to be the set of colorings that are invariant under the action by the induced map. Pi star. Well, written in words that way, again, I've used the word action here. This has a specific meaning for groups. There's a notion of a group action. I'm not going to define it because our textbook doesn't worry about it in this case. It's going on in the background, even if we don't talk about specifically and give a name to it. It's an example of a more general thing, but if you want to make it short and sweet, groups live to act on things. Okay, groups live to act on sets. So group actions are basically the entire purpose of a group in the first place. The description that we've given of the group determining equivalence of configurations, that is a notion of the group acting on the set of configurations. Okay, that action is, you can think about it as acting on the left by multiplication, if you want to think about it like that, or in evaluation, in this case, composition. So what is this? If I write it using set builder notation, this is the set of colorings in C such that pi star of C is C. That's what we mean by it is invariant under this action. So for this permutation pi, you're looking for all colorings that pi star fix or fixes. Okay. This is called the invariant set. It's the invariant set of the permutation pi in C. The reason we say in C here is, notice this is a subset of C. Okay. Okay. Similarly, given a coloring little c, define G sub C to be the set of permutations in G for which C is a fixed coloring. A set of permutations in G for which C is a fixed coloring. So this is kind of like the dual object, or you want to think about it as opposite, that's fine. It's like the dual object to how we defined it here. Here, we fixed a permutation and considered the set of all colorings that were fixed by that induced map of that permutation. Here we're going to do the same, except we're fixing a coloring and asking for the set of permutations for which that coloring is a fixed coloring. So instead of being a subset of C, this will be a it actually turns out to be a subgroup of G, but it's certainly a subset of G, just by definition. So it is the collection of permutations for which this is the case for that fixed coloring C. This is called the stabilizer. This is the stabilizer of C in the group G. Okay. This is always a subgroup of G. Okay. And lastly, let let's say C bar be the set of colorings in C that are equivalent to C under the action of the group G. So this is the set of colorings in C, or sorry, in big C. I wrote little c there, that are equivalent to little c under the action of the group G. This is a fancy and precise way of saying what we've been saying the whole time, that equivalent colorings are related by one of these symmetry permutations. Okay, so set of colorings of C that are equivalent to C under the action of the group G. Writing this in set builder notation, this is the collection of all of the images of this induced map for all the permutations. So what is this? This is really the equivalence class of C under this relation. This is just a quick way of writing the equivalence class of C under this equivalence relation that we defined yesterday, that we denoted by tilde, which is the default symbol we use for just a generic equivalence relation. This is also called, in words, the orbit of C under this action of G. You go back to our example with the 4-beaded necklace, and you'll understand why it's called the orbit, because consider what an equivalence class does, right, for this thing. If all you're thinking about is rotations, it takes a position, and if there is symmetry present, right, you can think of, for instance, the colorings. Maybe we'll go back where I had written out all of these equivalence classes here. So this is previous work. Equivalence classes. Think about what permutations take me to the next. So like how are these two equivalent? These two are equivalent by doing the permutation that sends this G here and basically pushes every coloring here indicated by this character string to the left, right? So this G goes over here, this G goes to the first position, this G goes to the second position, this R goes to the third position, this G goes to the last position, right? You could write out what permutation that is, and I can keep going here, right, until I've pushed R all the way to the front, and then I keep going again, and I have now pushed it back to the end, and so I have orbited around my configuration, right? So this is a way to think about this as this word is intuitively nice because it kind of tells you what is happening. As you're hitting these colorings with successive permutations, elements of G, they are sending it further around the cycle in that example. Okay, so it is orbiting around the cycle till it orbits back, right, to its starting position. Okay, so all those things are nice. Let's do an example here using the same C. So when I say let C be as before, what I mean by that, and I'm not going to rewrite this, so this is our example of the 4-beaded necklace with colors red and green. We are only talking about rotational symmetry, so our group is the cyclic group. Here is the set of all colorings. There's what it looks like. Once we had defined what equivalent colorings were, how that was handled, we saw that this had equivalence classes of this form. So, what is the orbit of, say, GGGR? Let's do that one. So, what is the orbit of GGGR? According to this definition on the previous page, the orbit of an element is just the equivalence class of C under that equivalence relation that relates them by this action of the symmetry group. So, what is that? What is the equivalence class here? Well, I know what the equivalence class is because I've already figured it out, right? The equivalence class of GGGR is this equivalence class. It's this one. Why? Because that's the one it's in. Notice that this is the same as the equivalence class of GGRG and GRGG and RGGG, right? And so this is simply the equivalence class containing GGGR, GGRG, GRGG, and RGGG. And if I had chosen any other of those, I would get the same orbit. So this is the same as the orbit of that element, GGRG. Okay, what is the orbit of GRGR? The orbit of GRGR, let's go here. Where is GRGR? It's here. Its equivalence class only has 2 elements, GRGR and RGRG. Let's see. What is the stabilizer of the element GGGR? Well, remember, what is the stabilizer? The stabilizer, fixing some coloring, some arrangement. The stabilizer of that arrangement in G is the set of permutations in G for which C is a fixed color, or a fixed coloring, or a fixed arrangement. So here, this coloring or this arrangement C is GGGR. So the question is, for what permutations is this a fixed coloring? Well, I can, of course, the identity permutation always fixes this, so that's always going to be included in the stabilizer. The question is, which contributes to why the stabilizer is always a subgroup. Um, what is the other permutation for which this is fixed? What am I allowed to do? Well, I am allowed, first of all, I can't move R, right? This can't move. So that has to be fixed. So looking at our permutations, of course, this means that if I'm permuting, you know, 4 objects here that I've labeled, R being in the last slot, 4 has to be fixed, right? So 4 would have to be fixed. And so in my cyclic group on 4 objects, I'm looking for something that fixes GGGR. 4 has to be fixed, so whatever permutation I write down here has to fix 4. What is the one that is going to work? What if I do this one? So 1 goes to 3, 3 goes to 1. 2 is fixed and 4 is fixed. That's fine, right? That's okay. What else? What else can I do here? Well, this is it. Okay, this is it. This is the only one. Okay. The others have to, the other elements in G have to change this. They can't fix this. These are the only 2 that do. Okay, next. What is next here? What about the stabilizer of GR? What is that? So again, the identity permutation fixes it. What else? Of course, I can swap the G's and swap the R's. That's not going to change anything. So that would be 1, 3, 2, 4. Okay. I could just swap the G's. I could just swap the R's. And that's it. Now what I want you to notice is that the product of the size of this equivalence class with the size of its stabilizer is what? So the size of its stabilizer is 2. The size of this equivalence class is 4. So this would be 4 times 2, which is 8. Then also notice that product of the size of the equivalence class and this other stabilizer we computed is 2 times 4, which is also 8. What's the relation there? Oh, well, let's alter something. In the example that we did before, we focused on just the rotational symmetries. Let's take the dihedral group instead. So we'll throw in the reflection symmetries here. Okay. So we'll throw in the reflection symmetries, because if we don't, this would be less interesting. Sorry. So if you're confused as to why I was including some of these things, this is why. So this is the problem with reusing old examples. So let's use the same previous example, except now our group is the dihedral group on these 4 vertices instead. So this, in both cases, is the size of the dihedral group on 4 vertices, and this is, the size of G. The question is, does this pattern hold? And the answer is yes. So lemma. So suppose a group G X on a set of coloring C for any coloring C and C. We have that the size of the stabilizer of C times the size of the equivalence class of C under this action is equal to the size of the group. Okay. Now, the idea in the proof, maybe I'll say proof. Here's the idea. We notice that every permutation in G why did I write lowercase g there? Every permutation in uppercase G can be written in a unique way as a composition of a permutation in the stabilizer with a permutation in a set P with whatever that set P is, the size of it is the same as the size of the equivalence class of C. We are done if we can show this. Why? Well, by the multiplication rule, right, our second way of counting things, if every permutation in G can be written in a unique way, that's important, of course, because if we didn't know this, we would have to worry about double counting, right? So if this was non-unique, we'd have to worry that when we counted the representations in this way, we've actually counted multiple representations for the same permutation. So we don't want that happening. So this can be written in a unique way as a composition of a permutation stabilizer with a permutation in a set having the same cardinality, the same size as this orbit set. And so you choose one, you choose the other. You're thinking about this composition as a product, or you can just say this is this is a sequential choice here. So this is we're using the product rule to count the number of ways that we're doing this, and so this is exactly the count that we get. So we're done if we can show that. So that's what we're trying to show. So so proof continued. Suppose that there are m, say m colorings. So m colorings in the equivalence class of C, which we'll label as C1, C2 out to Cm. Okay. For each I between 1 and m, let's choose a permutation pi sub I in G such that pi sub I star of C is equal to C sub I, and let P be the set of our M permutations, pi sub 1 out to pi sub m. So that we notice, of course, that this set P we've constructed has the same size as this orbit set. Okay. Now, let pi be a completely arbitrary permutation in our group G. Then what I know is that pi star of C is equal to C sub I for some I. I mean, it has to be one of the colorings here, right? So apply it to your coloring C. It's got to be one of them. There's no other choices, right? So it's equal to some C sub I. Okay. But if it's equal to that C sub I, since the pi sub i's that we've chosen are equal to C sub I, thus pi star of C is equal to C sub I, which is equal to pi star sub I of C. Thus, continuing on, pi sub I inverse composed with pi star of C is equal to C. Thus, pi sub I inverse composed with pi is an element of the stabilizer of C. Since it fixes C, what did I do here? I just composed on the left with pi sub I inverse. Remember, all permutations are bijections, ultimately, so they have well-defined inverses, right? We don't have to worry about them not having an inverse, right? They're always 1-to-1 and onto. They have an inverse, and we have used that fact here to get a thing, an object that fixes this coloring C, but that means it's in the stabilizer. Okay, but pi sub I composed with pi sub I inverse composed with pi is actually just pi. And this thing is in the set P, and this thing is in the stabilizer of C. So we're almost ready, right? Remember, our idea here was being able to write any permutation in a unique way as a composition of a permutation in the stabilizer with a permutation in a set P having the same size as the orbit set. We have done that. We just haven't shown that this is unique. So need to show this is unique. Meaning that there's no choice involved here that matters, right? So it wouldn't matter what choice, seemingly we have made choices. We have to show that those choices ultimately don't matter, and that no matter what choice we made at each step, we would always end with the same representation of pi. Again, the reason why this is important is because we're thinking of counting these things, right? So if there were multiple different representations here, you have to worry in the count that you're double counting representations for like a single permutation, right? So you're getting something that's wrong, that's not accurate, not an accurate count. So we got to show that this is unique. Okay. So then so suppose that we have done this in two distinct ways. So suppose that pi has been rewritten as pi sub I composed with sigma, and also it's some pi sub j composed with tau, where these pi sub i's, pi sub j's come from the set P, and the sigma and tau come from the stabilizer. Okay. But if this is the case, this means that pi sub I of sigma of C has to be equal to pi sub I of C, because sigma is in the stabilizer. So sigma of C is C. It fixes C because it's in the stabilizer. That's the definition of the stabilizer. Okay, but pi sub I of C is C sub I by definition of these things. And similarly, pi sub j of tau of C is pi sub j of C, but that's again because tau is in the stabilizer, so tau of C is C, it fixes C. But pi sub j of C is C sub j. But according to this, these two things have to be equal. C sub I has to equal C sub j. But we did all these choices for, these are all distinct colors here. That's the whole point of an equivalence class, is that it's all these are the distinct colorings here. They're in the same class, but they are distinct in the sense that if two are equal in this way, the only way that can happen is I is equal to j. If I is equal to j, then sigma i's are equal. The sigma and tau, the pi sub I and pi sub j's are equal, and so the sigma and tau, these have to be the same. This has to be unique, right? So must be unique. And when I say it, I'm referring to this representation of our permutation. It has to be unique, and so by the multiplication rule, by the product rule, this count matches up. The size of G is the size of the stabilizer times the size of the orbit. Okay. This leads us to the following, which is that it turns out that the number of equivalence classes which is what we're interested in, we'll call it N maybe, is, so equivalence classes of colorings is the average size of the invariant sets. So remember, we defined what an invariant set on a coloring was. So here's this fact is called Burnside's lemma in our context. So we'll call this a theorem, which is popularly called Burnside's lemma. Which tells us the following. The number of equivalence classes N of the set C in the presence of the group of symmetries G is given by N, which is, I said that it's the average size of the invariant set, so we're averaging over elements of G, so this is 1 divided by the size of G times the sum over elements of G, which are permutations in G, of course, of the sizes of these invariant sets for the permutations. Just to remind you, we defined the invariant set thusly, right? So for a permutation in G, the invariant set C sub pi is the set of colorings that are invariant under the action of the induced map pi star. So it's the set of colorings that are fixed by this induced map pi star for my permutation pi in G. This is like the dual thing, right? It's we fix a permutation and then it's a set of colorings fixed by that induced map. Whereas the stabilizer was we fix a coloring and then it's the set of all permutations whose induced map fixes that color. Okay. All right. So then, proof of Burnside's lemma, and then we're going to apply it to actually solve these problems. So if P is a logical expression let square bracket P be 1 if P is true, and square bracket P be 0 if P is false. Then let's start with this expression on the right and come up with a way in which it's actually counting the number of equivalence classes. So the expression on the right is 1 over the size of the group G times the sum over permutations in G of the sizes of the invariant sets. Going to rewrite this as the sizes of the invariant sets. So this is going to be 1 over the size of G times, we can rewrite this as a double sum. So this is a sum over permutations in G, and then a sum over the elements in C, the colorings in C, and I have the logical statement here, pi star of C is equal to C. Let's think for a second about this equality here. Counting the size of this invariant set, here's the invariant set. The size of this is the number of colorings fixed by pi star, which is the number of times in this sum this statement is true. Since I'm summing over all of the colorings, if, let's say, for instance, that for a given permutation, this set had 2 elements, right? Then there are 2 colorings for which this statement is true. In this sum, I would get 1 for one coloring when it's true, and another 1 for the other coloring when it's true. Taken together in the sum, this would be 1 plus 1, or 2 for those particular colorings, satisfying this for that permutation pi. And I would do that for every permutation, summing over all the colorings every time. So this is just a way of enumerating this set. Okay, so that's what's going on here. Now, of course, I can swap the order of this summation. And this equality holds. So I can swap the order of this summation, and this still makes sense. But now we have altered this ever so slightly. In fact, which is why I talked about this being the dual statement. In fact, all we've done here by swapping that order is we've basically gone from fixing C summing over pi versus fixing pi summing over C. Fixing C, the object we get when we fix C is the stabilizer, but it's the same object now. We're just doing it from like the dual direction, right? We're fixing C and looking at this object. We're looking for permutations satisfying this statement. Here, it's the same underlying statement, but we fixed a permutation, and we're looking for the colorings that satisfy this statement. Okay? And so this is enumerating the stabilizer of C. This is a sum over colorings of the size of the stabilizer. But hey, the reason why we want to do this sort of thing is because we just proved a lemma just a second ago that tells us something nice about that. It tells us that the size of the stabilizer is the size of the group divided by the size of the orbit for that same. So the size of the stabilizer for C is the size of the group divided by the size of the equivalence class of C, or the orbit of C. And so this is going to be replaced with here. This is what I replace it with. This size of G is going to cancel out with that size of G and leave me with the sum over C and C of 1 over the size of the orbit of C. Okay. But what is this? Well, I can rewrite this sum. This sum's a little confusing because the sum over C, but then C bar shows up. I have to think about how that is, right? So this is the same as if I sum over C bars, where I then sum over colorings in little c bar, this same thing. What is this statement here? These two things are really just reinterpretations of the same thing, because you're just unpacking what this would mean in notation, summing over all colorings of C. Here I'm summing over equivalence class is C bar, and then summing over all the colorings in an equivalence class, these things. But this is the reason why I've rewritten it in this form, is that it makes it easier to see that this is a sum over equivalence classes of 1. You get a 1 for each equivalence class. We're done now. From this, we're now immediately done. This is the enumeration that we wanted. But I want to say, why is this equality holding? Let's look at the example that we did previously. So here, this example, right? You have one object in your equivalence class, right? And so 1 over the size of C bar here is 1 over 1, which is just 1 for this. But there's only a single coloring here. So you just get 1 as your contribution for this. Here, you would get 1 over the size of C bar, in this case, is 1 over 4, right? But there's 4 colorings. So this is 1 over 4 times 4, so 1, again, is the total contribution in the sum. If you like, you could view it as a sum, 1/4 plus 1/4 plus 1/4 plus 1/4. That is what we're doing when we rewrite it this way, where we have a term here for each coloring in this equivalence class, and it's 1/4 for each because 4 is the total size of the equivalence class. So same thing is true here. You would get 1/4 plus 1/4 plus 1/4 plus 1/4, which would also give you 1. Here you would get 1/2 plus 1/2 because, again, the size of this equivalence class is 2, but you only have 2 colors. So here, again, you get 1/4 plus 1/4 plus 1/4 plus 1/4, so 1. And here you get 1 times 1 because there's a single element and there's one of them, so one term. In each case, you're getting 1 for each equivalence class. That is what this equality means. But 1 for each equivalence class, this is just the number of equivalence classes, or n, and that is it. Okay? So that is it. That's Burnside's lemma. And now, the point. The first time we actually apply all of this new terminology, this new machinery, all this group theory stuff, we can actually answer a question now. So let's apply it to solve these problems that we described before. Okay, so example, round table problem. In the round table problem, remember how we had this stated. So the size of the group in the round table problem is n, because this is the cyclic group, right? On n vertices. Okay, the invariant set of the identity permutation is everything. That's the entire set of colorings, right? The invariant set of a pi where this pi is any non-trivial permutation, that is a rotation in this case. Any non-trivial rotation, what is the, when we say non-trivial, we mean anything that's not the 0-degree rotation. So anything that rotates by some actual positive amount here is empty. Why? Well, because such a permutation moves things. It's not going to fix. It is not going to fix any of the it's not going to fix anything here. It's going to be empty if this is non-trivial. And so, by Burnside's lemma, the number of non-equivalent seating arrangements is equal to, this is the sum, this is 1 over size of G times this sum over the permutations of G of these invariant sets. But this sum only has a single term because the size, the size of the invariant set of the identity transformation, of course, is just the size of C, which we know already. This is so the size of C is n factorial because it is the total number of seating arrangements. Remember when we restated these problems, right? First thing we did today, restating these problems. C is the collection of all n factorial seating arrangements. So that's n factorial. The size of any of these non-trivial rotation invariant sets is 0 because they're all empty. So this thing only has a single term. So this is n factorial over n, because the size of G is n. Size of C is n factorial. And so this is n minus 1 factorial. Okay. Let's do a specific necklace problem. Okay. Let's do 4 beads using 2 different kinds of beads. So example, necklace, 4 beads, 2 kinds of beads. So in this case, what is our set? So in this case, our set G is the dihedral group, or sorry, our group. G is the dihedral group on 4 vertices, and its size is 8. Okay. We need to compute all of the different invariant sets. So in this case, what are the sizes of all of these invariant sets? So there's the size of the invariant set of C sub the this is the invariant set for the identity permutation. What is this? Well, how many colorings do I have total? 4 beads, 2 kinds of beads. The total possible number of colorings would be 2 to the 4. Remember, C is the set of all m to the n possible arrangements of the m kinds of beads in the necklace. So m kinds of beads, so 2 to the 4 because there's 4 beads, right? So this is 2 to the 4 or 16. Okay. What about, we just have to go permutation by permutation. What's the invariant set for this transposition 1, 3? Well, it's actually the same as the invariant set for the transposition 2, 4, which is 8. We can verify this directly. You can check this yourself, or through a clever enough counting argument, you could see why these two work out in this way. What about these reflections? So 1, 2, 3, 4 and 1, 3, 2, 4. And 1, 4, 2, 3. What about the size of these invariant sets? These have size 4. And the 4 cycles, their invariant sets, so 1, 2, 3, 4, this is the same as the invariant set for 1, 4, 3, 2. These both have size 2. Remember what an invariant set is and what you're being asked, right? This is, you are fixing the permutation and counting the colorings fixed by that induced map, right? Can you spot, well, you know all 16 colorings are fixed by the identity. Can you identify the 8 colorings total that are fixed by 1, 3, and 2, 4? Again, here, I'll put the full list of these colorings out for you. Where are they? We got them. Yeah, we got them here. So here's the full list. Right? Think about which of these are fixed by the permutations 1, 3, and 2, 4. Think about which ones are fixed by these. How about these? See if you can identify the two colorings fixed by these two. Okay. And so, once we have done all of this by Burnside's lemma, Burnside's lemma implies that n is 16 plus there's two terms in the sum which are 8, so that's 2 times 8. Plus there's three terms in the sum which are 4, so that's 3 times 4. Plus there's two terms in the sum which are 2, so that's 2 times 2. And we're dividing all of that by the size of our group, which is 8. And this is 6. So there are 6 such necklaces. Okay, let's do one more example. We'll do 3 bead necklaces. 3 colors. So 3 colored beads. Or I should say 3 colors for beads. 3 colors of beads. Okay. So now we have 3 beaded necklaces. What is our group? It's the dihedral group on 3 vertices, which has size 2 times 3, so 6. Okay, 3 bead necklaces. What things do I need to compute? I need to compute the size of all these invariant sets. So the colors here, we have 3 beads, 3 colors to choose from for each bead, so 3 times 3 times 3, so 27 total. Right? We're just going down the 6 elements of this thing here, right? So for these transpositions, 1, 2, and 1, 3, and 2, 3, that's all of my transpositions here. There's 9 colorings that are fixed by those things. Think about, again, how to count these looking at your total list. Okay, might be instructive to, even though it's kind of annoying because there's 27 of them, but still actually writing out every single one of these things can be a little bit instructive as to how this goes. How about the 3 cycles? And what about these? There's 3. Hopefully you're seeing now how this works, how this pattern goes. Okay, thus, by Burnside's, n is, we're going to do the same thing here, so this would be 27 plus 3 times 9 plus 2 times 3, which is 27 plus 27, that's 54 plus 6 is 60 over the size of the group, which is 6, so this is 60 over 6, which is 10. So there are 10 such non-equivalent 3 beaded 3 colors necklaces. Okay. All right. So we finally at least showed how we can bring this group theory stuff to bear on some of these problems that we had. But and note that maybe I should write it on this previous page since I had still had some calculations. So note that in each case, to use Burnside's lemma, we need to be able to compute the size of these invariant sets. For every permutation in the permutation group. But actually, it turns out that in many situations, this is easy to compute. Once we notice something. Okay. So what is it that we are noticing here? Okay. Well, suppose we wish to determine the number of ways, so to count the number of ways to color in objects using up to m colors, discounting symmetries. Discounting symmetries of some symmetry group G. Okay. Now notice if a coloring is invariant under the action of a permutation pi in G, then every object permuted by one cycle in pi must have the same color. So think about that for a second. So thinking of cycle notation, right? A permutation is made up of at least one cycle, right, that you can think of. In fact, we can say that here, using cycle notation a bit later, like expanding on what we normally do, remember, when something fixes a thing, we can write that as a one cycle, which is just, parentheses around a single number indicating that that thing is being fixed. So even that is a cycle. So of course, the point is, yeah, this thing can be written as a bunch. Think about if a coloring is invariant under the action, means it's fixed by the induced map. Okay, then every object permuted by one cycle in this same permutation must have the same color. Okay, because if it didn't, it wouldn't be, the coloring in question wouldn't be invariant with respect to that, permutation. So, thus, if pi consists of k disjoint cycles, The number of colorings invariant under the action of pi is the size of that invariant set, which is m to the k. This is the thing that we notice. This is very important here. Now, the thing to notice is if we go back to these examples, hmm. Going back to this example, seems I could have done this using this new fact in this way, but you're going to raise your hand, right, metaphorically here and say, wait a minute. The permutation here is one cycle. It consists of one disjoint cycle. So why are you saying that both of these consist of three disjoint cycles? 1 to 3. Let's give myself some. Maybe I'll just I'll just do it up here since we're not going to use this sheet again. 1 to 3 is really that in cycle notation. We just suppress the one cycles typically. In the same way, 2, 4 is 2, 4, 1, 3. 3 cycles. 3 disjoint cycles in both cases. And thus, why this is 2 cubed. Here, in all cases, we have 2 disjoint cycles, so it's 2 squared. Here, in both cases, we have 1 disjoint cycle, so it's 2 to the first. And so this illustrates, again, here, this other example that we did, right? This was 3 cubed, 3 squared, and 3 to the first in the same way. And so, this is a very nice fact here. So, in our example, just to do it again, if S is a set of vertices of square, and G is D4, then the invariant set of 1, 2, 3, 4 is, how many of those are there? Using M colors here, this would be M. Okay, for a permutation consisting of 2 disjoint cycles, this would be M squared. For a permutation on 4 letters consisting of, we'll do like 3, 4, like here, this would be M cubed. Again, notice that normally we suppress 1 cycles, but here we can't. We have to actually list them out. And then, of course, for the identity transformation, yes, I know normally we write it as C to the first, or C sub just 1 with parentheses here, just our usual notation for the identity. These are 4 disjoint cycles, so this is M to the 4th. So if you were wondering in our examples going back why I wrote this as 2 to the 4th, well, there's 4 disjoint cycles here, right? It's just we were suppressing the notation. So we have to actually think of it like this so that we can count these in this way. Okay, so we have to actually include the length 1 cycles when we do this. Okay, I'm going to give a definition of a single thing, and then we'll be done for today, and we'll finish up tomorrow with this stuff. So this is the cycle index. So the so for permutation pi in G, define a monomial, we'll call it m sub pi, associated with pi in the following way. If pi is a product of k cycles and the ith cycle has length L sub I, let m right like this. Let m sub pi be the monomial m sub pi applied to variables x sub 1, x sub 2, and so on out to x sub n. To be the product, remember this is a monomial supposedly, so I equals 1 to k of x sub L sub I. Okay. The cycle index of a group G of permutations on n objects is the following. It's defined as P sub G of the vector x, which is 1 over the size of G times the sum over all permutations pi in G of these monomials we defined above, where x is the vector x1, x2 out to x sub n. Okay. We'll do an example of this tomorrow and see an immediate application. Okay. And then we will get the big payoff we've been waiting for with all this group stuff, which is just a really, really nice way of using this stuff to enumerate some pretty complicated counting problems, or enumerate configurations involving like some pretty complicated situations that otherwise you'd have a hard time figuring out how to go about counting these things. So we'll see an application of this stuff tomorrow. I'll state Polya's enumeration formula, and we'll do a few examples, and that will be that. Then we will we'll finish up our discussion of that, of the group stuff. We'll do some stuff with the Stirling numbers, so Stirling cycle numbers and Stirling set numbers, and then that will basically be the course. That will basically be everything. So anyway, that is the plan. So I will see you all tomorrow as we wrap up. This is like the last couple of topics we have to wrap up for the course. So anyway, I will see you all tomorrow.